The discovery of even the simplest life on Mars would be the most devastatingly bad news for humanity. And the absence of news is, in fact, good news. This is the view put forward by Oxford University philosopher Nick Bostrom. If life arose independently twice in our own solar system, yet we see no evidence of advanced civilizations anywhere, it implies that almost all civilizations are eliminated by some great filter before they can reach a high technological stage. This would be the stark confirmation of the filter's brutal effectiveness. If life is not rare to begin with, the bottleneck that prunes civilizations must be higher up, which, conversely, only highlights how rare the Earth is for having made it this far. And that leads us to the other possibility, that life on Earth is truly alone in the cosmos. Hello, Earthlings. I'm Old Horse. And today, we're going to discuss the ultimate isolation, the rare Earth hypothesis. Carl Sagan once said, "Astronomy is a humbling and character-building experience." So far, decades of searching have failed to turn up a single definitive radio signal confirming the existence of extraterrestrial life. Of the thousands of exoplanets we've discovered, not one has an atmospheric composition suggesting the presence of life. But the numbers don't lie. There are tens of sextillions of stars in the universe, each potentially with its own system of planets. The idea that Earth is the only place in the entire cosmos with life seems utterly counterintuitive. Could the conditions for generating life be so incredibly precise that Earth is the single, unique place in the whole universe that allowed life to survive long enough to evolve intelligence? This is the core proposition of the rare Earth hypothesis. We know how vast the universe is, how immense the star count is. Even with an astronomically low probability of life forming, there should theoretically be a staggering number of civilizations out there. Yet, we see no sign. Why? And a simple question posed by Enrico Fermi, "Where is everybody?" became the biggest question of the century. The Fermi Paradox. There are millions of proposed explanations for the Fermi Paradox, ranging from interstellar predators hunting other civilizations to the idea that we are kept in a galactic zoo by aliens. But to seriously discuss the problem, we must consider the simplest answer. We haven't found aliens because they don't exist. In the field of astrobiology, we have a sample size of 1. Life on Earth. All life we know of is dependent on DNA, carbon, and water. While life forms entirely outside our definition may exist, we must use Earth's life as our frame of reference. Life on Earth emerged quickly. Single organisms appeared within a few 100 million years. These macroscopic organic machines that could but they remained that way for more than 2 billion years before the emergence of the eukaryotic cells. Possess organelles to perform specific functions, such as a nucleus and mitochondria, meaning the single-celled organisms began to get complex. This one step took 2 billion years. 600 million years ago, multicellular life appeared. This means for 87% of life's time on Earth, it was simple, single-celled organisms. It took 3.9 billion years for life to make this jump. But then, something incredible happened. 540 million years ago, just 60 million years after the appearance of multicellular life, the Cambrian explosion occurred. Hundreds of millions of different species burst forth in the oceans. Plants and animals suddenly appeared, and all the animal and plant life on Earth today can be traced back to these sudden emergences. Think about it. 4 billion years of quiet, followed by an explosion of evolution. When people discuss the Great Filter, the leap from single-celled to multi-celled life is unquestionably one of the monumental filters that life must cross. How rare is this one step? How stable must a planet's environment remain to make that leap after 4 billion years? The question forced many scientists to consider, what if we are truly alone? What if the conditions for intelligent life are so restrictive that they only happened here? And if so, what are those conditions? In 2000, Peter Ward and Donald Brownlee proposed this view in their book, Rare Earth: Why Complex Life is Uncommon in the Universe. The theory is now known as the Rare Earth hypothesis. The hypothesis outlines 5 major core supports, plus 3 key supplementary conditions. We are all familiar with the circumstellar habitable zone, the distance a planet must be from its star for liquid water to exist. But there may also be a galactic habitable zone, and we are sitting right in it. The Milky Way is a large galaxy. For a long time, it was thought that life was more likely to be found toward the center of the galaxy because of the frenetic activity there. The problem is that activity produces tremendous amounts of radiation. Hubble images of the Andromeda Galaxy show that the galactic core is a crucible of massive stars. Supernova, hypernovae, gamma-ray bursts, and black holes. All this activity releases staggering amounts of radiation that would likely sterilize any nearby planets. At the very least, there would be no night if you lived there. We are a great distance from the galactic core, sitting, in fact, between two spiral arms. This position keeps us far from the chaos of the spiral arms and star-forming regions, while still allowing us to take advantage of the heavier elements ejected by supernova explosions. Furthermore, the density of stars here is lower, reducing the chance of other stars passing close enough to gravitationally disrupt our orbits. Are we sitting in a Goldilocks zone of the galaxy? If this is a necessity for life, then the vast majority of stars in the Milky Way are eliminated. The Sun is classified as a G2V star, a main sequence star. This means it is stable for a very long time. Its size and temperature are also ideal for life. Larger, hotter stars have a habitable zone, but they emit a great deal of ultraviolet light that can ionize a planet's atmosphere. Smaller red dwarf stars require planets to orbit very closely to be in the habitable zone, which leads to tidal locking, a condition unfavorable to life. Even an identical star to our Sun has a time limit. Stars begin active, fluctuating in brightness and intensity. They settle into a long, stable period, and eventually become red giants and collapse. This stable middle period is the golden age for life, and thankfully, it lasts for billions of years. Yet, after excluding stars in the galactic badlands, stars that are not the Sun's type, and stars that are too young or too old, the number of potential life-bearing suns shrinks dramatically. And that's just the beginning. Once you have the right star, you need the right planet in the habitable zone, meaning a rocky planet. Our solar system has 4 rocky inner planets and 4 gas giants. We once thought this was the normal configuration. The dense rocky material would clump in the center, and the gas giants would form further out. When we began to search for exoplanets, we assumed we would find this same pattern, but we didn't. A team led by Lauren Weiss at the University of Montreal, using data from the Kepler Space Telescope, studied 355 stars and 909 orbiting planets. They found that most exoplanets are about the same size and are evenly spaced. Our solar system is dramatically different, ranging from Mercury, which is moon-sized, to Jupiter, which is 1,000 times bigger than Earth. The distance between Saturn and Jupiter is the same as the distance between Jupiter and the Sun. The distance between Uranus and Saturn is about the same as the distance between Saturn and the Sun. The distance between the planets grows almost exponentially as you move out. This extreme difference in size and distance makes our solar system an outlier. It forces us to rethink the formation of our solar system and why it's so different from other planetary systems we've found. In fact, the pattern of planets around other stars makes our solar system look almost like the combination of 2 systems, an inner solar system and an outer solar system, with Earth sitting in the sweet spot of the inner habitable zone. Could this unique planetary configuration be a factor in Earth's ability to harbor life? It is highly likely. Space is filled with asteroids, comets, and the interstellar objects we are now discovering. Any one of them could strike Earth and disrupt the stable environment required for life to form. Fortunately, we have Jupiter, the big guy, acting as an interstellar Roomba, vacuuming up a huge amount of these objects. In 1994, comet Shoemaker-Levy 9 slammed into Jupiter, and the Hubble telescope captured the event live. It was one of the most incredible things I've ever seen. The impact left an Earth-sized scar on Jupiter's surface. Another impact scar appeared in 2009. So, the vacuum cleaner effect is real. In fact, One study suggests that Jupiter is hit by comets and asteroids 2,000 to 8,000 times more often than Earth. Without Jupiter's protection, Earth would be constantly bombarded by these objects. The asteroid that wiped out the dinosaurs would be a regular occurrence without Jupiter. Life would be reset again and again, and would have no chance to evolve. And Jupiter is just one of 4 gas giants that create a multi-layered shield. It is ironic that the largest impact in Earth's history, the formation of the Moon, may have been the best possible break for life. The key is that the Moon is incredibly unique in our solar system, and may have played a critical role in the emergence of life on Earth. It stabilizes Earth's axial tilt and also provides the tides, which may have been key to life's formation. One idea is that as water evaporates from tidal pools, organic compounds are concentrated, and this may have been the birthplace of the first self-replicating cells. But how rare is this phenomenon? We do not see it elsewhere in our solar system. The moons of Jupiter and Saturn are larger than ours, but no planet-to-moon size ratio is comparable to Earth and the Moon. Mars is the other rocky planet with moons, but they are more like captured asteroids. Pluto and Charon are really just 2 dwarf planets orbiting each other. The only plausible explanation for this unique situation is that a Mars-sized protoplanet struck Earth at an oblique angle, stripping off material that eventually formed the Moon. Evidence from lunar rocks backs up the theory. This happened once in our solar system. It's hard to judge if this is the case around other stars, as we only confirmed the first exomoon in 2018, and it was a Neptune-sized moon orbiting a gas giant. Other key conditions: a strong magnetic field. Earth is the only rocky planet in the solar system with a strong magnetic field, generated by an internal dynamo, a molten outer core spinning around a solid sphere of iron and nickel. This strong magnet effectively shields life on Earth. Do rocky planets around other stars commonly have strong magnetic fields? We don't know, but given our solar system, there's no reason to assume it's common. Plate tectonics. Earth is also the only planet with plate tectonics. Most rocky planets and moons have a liquid layer beneath the surface, but only Earth's plates are fractured, allowing overheated gases to vent into the atmosphere, making it thick enough to sustain life. On Mars, for example, magma exists below the surface, but it just erupts repeatedly in the same place. That's how Olympus Mons was formed. Earth's crust, however, is constantly renewed. Crustal plates subduct, melting and taking organic molecules produced by surface life with them, and then venting them back out through fissures. This is thought to help circulate minerals, making the soil more fertile and better for life. A particular primordial atmosphere. Early Earth's atmosphere was toxic, full of methane, sulfur, ammonia, carbon monoxide, and even hydrochloric acid. Not a great place for a holiday. But this specific cocktail of ingredients may have been the necessary feedstock for life to form, a mixture that may be exceedingly rare on other planets. In short, the emergence of intelligent life on Earth required an incredible, interlocking series of special conditions. We take these conditions for granted because they were here from the start, and thus assume they are universal. But as we explore the cosmos, we are beginning to realize they are not common, they may be incredibly rare. In fact, they may be so unique that they are one of a kind in the universe, and we may be completely alone. It is a sobering thought, and one that we currently have no evidence to disprove. Of course, not everyone is so pessimistic about the hypothesis. Many rebut the rare Earth hypothesis, calling it an eccentric view of life. As I mentioned, we have only one sample of life, and we are looking for something similar to life on Earth. But there could be life forms entirely outside of our definition. Another possibility is that Earth itself is an outlier planet. Perhaps we are the odd ones out in the cosmos. For many, the number problem remains the core issue. The number of stars in the universe is so vast that the probability of us being alone is just too small to be credible. Look at the famous Hubble Deep Field image. Every tiny pinprick of light is a star. Each of those stars could have multiple planets. Even an unbelievably small probability does not equal 0. It seems naive to think life has never arisen in such a vast cosmos. Perhaps the universe isn't filled with intelligent life, and the existence of intelligence on Earth is merely a blink in the history of the cosmos. It took Earth 4.6 billion years to produce us. Whether we will survive another billion is an open question. So, it is possible that the universe has contained millions of intelligent species that have simply faded away, which would be explained by the Great Filter. It is also possible that interstellar travel is simply impossible. The distances are just too great. Or, perhaps the history of the galaxy and the universe itself is like a string of blinking Christmas lights, where life has come and gone at different times, never to overlap. This is why the discovery of a microbe on another body in our solar system would be the most contradictory great discovery in human history. It would utterly transform our understanding of life, proving that it's not unique to Earth, but it would also brutally confirm Bostrom's fear. Life is not rare to be born. The truly rare thing is the intelligent civilization that manages to survive the Great Filter. So, do you believe Earth is the lone survivor to cross all the thresholds? Let me know your cosmic views in the comments below.